3.7 Derivatives of inverse functions. The theorem to begin with here is let f of x be a function that is both invertible and differentiable. So it has an inverse, and it also has a derivative. Let y equal f inverse of x be the inverse of f of x. For all x satisfying f prime of f inverse of x not equal to 0, dy dx is the derivative of f inverse of x is 1 over f prime composed with f inverse of x. Now, all on its own, that is a fairly confusing topic. I mean, you just look at it and it just looks crazy. So let's unpack this a little bit. Example 1, use the inverse function theorem to find the derivative of g of x equals x plus 2 over x. Now, we want to think of this function g of x as the inverse of some other function f. So I'm going to go ahead and write f inverse of x, just so I can think of it as the inverse of f. So the inverse of g of x is f, which is 2 over x minus 1. By way of some algebra, we can show that that is true. All right. Now, according to this theorem, what we need to do is find f prime and f inverse. Well, we already know f inverse. It's x plus 2 over x. So let's first, based on that theorem, g prime of x equals 1 over f prime of g of x. All right, so f prime, if we use the quotient rule, actually the power rule would work here along with the chain rule, so negative 2 over x minus 1 squared. All right, so that's f prime of x. So f prime of g of x, is negative 2 over x plus 2 over x minus 1 squared, which, with a little bit of algebra, we can determine that is negative x squared over 2. By the way, convince yourself of these steps. I'm saying you can use algebra and do it, but really convince yourself that they're true. I did on my own. All right, so that means over here, back over here at g prime, that is 1 over negative x squared over 2, or negative 2 over x squared. So that is the derivative of g of x. That is our derivative. Now, you can take the derivative directly using the quotient rule of x plus 2 over x, and you should arrive at that same conclusion. Use the inverse function theorem to find the derivative of g of x equals the cube root of x. Now, you might recognize this as x to the 1/3. However, we don't know yet that the power rule does in fact work for rational functions. So if we didn't know that fact, okay, so keep that in the back of your mind. If we don't know that fact, well, we can automatically say, if this is f inverse, that f of x is x cubed. So based on the inverse function theorem, we can say that g prime of x equals 1 over f prime of g of x. F prime of x equals 3x squared, which means that f prime of g of x is 3 cube root of x squared. I'm going to go ahead and write that as 3x to the 2/3, which means g prime of x is 1 over 3x to the 2/3, or if you'd rather, 1/3 x to the negative 2/3. Now, at this point, I can say, look, I could have just taken the derivative using the power rule. Bring the 1/3 down, subtract 1, you get negative 2/3. This is what allows us specifically to make a more general statement that the power rule does work. Now, the book actually proved this. OpenStax Calculus Volume 1, they proved that the power rule works for any n, any value of n, in the real numbers. You might check that out because it's actually a really neat proof. But for now, going forward, we can say it does in fact work. All right. Example 3, find the equation of the line tangent to the graph y equals x to the 2/3 at x equals 8. Well, our slope is dy dx evaluated at x equals 8. Based on our power rule saying that it does in fact work for rational exponents, we can say that is 2/3 x to the negative 1/3 evaluated at x equals 8. The cube root of 8 is 2, so this is 1/3.